So I'm Gursimran. I'm a research engineer at Aspiring Minds, and this is a startup which is based in India, and this is like one of the world's biggest, largest employability assessment firm. So my co-author, I have done this work jointly with Shashank Shrikant and Varun Agarwal. So Shashank is a senior research engineer at Aspiring Minds, and Varun is the CTO of the company. So this work is related to the grading of programming codes. And today I'm going to tell you that how do you build scalable machine learning models to automatically grade computer programs. So this is the structure of my presentation. First, I'll talk about the motivation of the problem. And then I'll talk about some traditional methods of how do you solve this problem. And then I'll talk about the quotient-specific machine learning models, which is the earlier work that we have done, presented in KDD 2014. And that is a kind of a background to this work. And then I'll talk about the current work, which is quotient-independent machine learning models. So why do you assess programming codes? So out of all the skills to assess, one thing that has got a lot of traction recently is programming codes. So there are multiple efforts going on to teach programming to both kids and adults, and it's very important to assess these learners, both in terms of giving appropriate feedback and also to ensure meritocracy in the programming job industry. So traditional methods include manual assessments and test suite-based approach. Well, manual assessments is perfectly fine if you have a bunch of programs, but it really becomes hard when you have to grade thousands of programs together. On the other hand, test suite-based approach is scalable, but the point is that it's good to tell which programs are correct, but you get little insight into programs which are not correct. And moreover, if you do a small silly mistake, then that can really bring down your score, and a person may be penalized unfairly for this. So we did a case study at Aspiring Minds, and we found that like 15 to 20% cases where the person has committed a small silly mistake, his logic was all right, but he was unfairly penalized by the test suite-based approach. So this is why if you ask a seasoned interviewer, he'll tell you that he'll hardly look at the number of test cases that your program passes, but more about what is the logic and the organization of your program. So this is the earlier work that we presented in KD 2014, and this is quotient-dependent machine learning models. So when you talk about machine learning, the very first question is, what are the features? So how do you extract features from the programming codes? We presented a very intuitive array of features in the last work, and these are based upon the control context and data dependencies in the program. So I'll just give you a brief overview of these features. So there are 5 feature categories. First is basic, examples like count of for, count of if, and they are like basic. The second example is basic control, and examples are like count of for inside for or count of if inside for. And then there are other kind of more complex features like expression dependencies, expression control, and these are like how the variables among two expressions are dependent on each other. So you can go through our work for more details on these features. So this is like a diagram of our earlier work in the quotient-specific model building. So once we have features for these codes, which can uniquely identify a code, and we also have human grades on these codes, we can pass these two into supervised machine learning loop, and we have these models. So these models can emulate probably a teaching assistant and can give you grades for ungraded codes. So this is how we grade ungraded codes. So these are the KDD 2014 results. And on the test set, you see with the test cases, together with the human grade correlation is 0.71. And with the machine learning output, we have a correlation of 0.86. And this is with the human graders. And this is like a significant improvement over the test case baseline. And you can see that this rivals between the correlation between two human graders. So even if two human graders grade the same code, they will have some discrepancies, and this rivals that result very, very well. So if it was so good, what is the problem? So here I present 2 programs. One is binary search and one is bubble sort. So you can see that in binary search, an important feature would be and how many if inside for are there. So these are the control context features. And in bubble sort, important features would be how many for inside for are there. So what this means is that definitely if you learn a model on binary search, you cannot use it for bubble sort and vice versa. These models are quotient-specific models, and these are hard to scale. So this is a diagram of the 2 approaches. The first, on the left hand side is the quotient-specific approach, and on the right-hand side is a new approach, which is quotient-independent. So here on the left-hand side, you can see that you need to build new models for each new quotient, and this is hard to scale. On the right-hand side, on the other hand, we just learn one quotient-independent model, and this model can learn even for any new unseen problem. So this is fairly scalable. So now in the rest of the presentation, I'll talk about how do we do this approach and how do we learn this quotient-independent machine learning models. So there are two main fundamental ideas of this paper. The first is feature transformation, that how do you convert the original problem-specific features into new type of features that can enable us to learn quotient-independent models. So we do this conversion from quotient-dependent to quotient-independent features. And the second idea is the automatic identification of good responses. So what are good responses? These are responses which solve a particular programming question correctly. This is the main. So first of all, I'll talk about the feature transformation. This is a very important slide. So the intuition over here is that, so we have to convert the features into features that follow the same structure across quotients. And by structure, I mean that they have the same relationship with output. With increase in the feature, the output decreases, or with decrease in the feature, the output increases. If such a feature, I can evaluate such a feature, it would be really awesome, and that feature, I can learn the model with that feature across problems, and I can have this quotient-independent model. Now, one example for this type of feature is the distance. It is the distance of any particular code from its good set, and good set is the set of all the good responses. So you can see that features like for inside for or if inside for will not satisfy this property of structural independence or structural invariance. Now this is a diagram representing the feature space, the multidimensional feature space. Here you can see the blue dots represent good codes, and these cluster together because they look similar. So if I talk about any given code, the distance of that given code from the good responses of that particular quotient represents the closeness of this response to that its good set. So this feature is structurally independent, it's structurally invariant, and if this distance is more, it means that it's far away from its good set, it's not like that. It means that its grade should be low, and if this feature is low, it means that the grade should be high, it's really close to its good set. So the question is that how do you get good responses? If humans were to create good responses, then how do you bring human out of the loop, and how does this really scale? So the second fundamental idea of the paper is that we exploit this property of this particular domain in which we can use test cases as a metric to get these good responses automatically. So we don't need any human graders here. We don't need any humans. We can just use this test suite, and we can get good responses from it. So once we have these good responses, we can have this distance metric, which is quotient independent, which is structurally invariant, and then we can learn these models across quotients. So this is like a system diagram of this. So on the bottom, you can see that the test case result is there. That goes into the test suite, and you have good responses, and this is identified automatically. And these good responses are fed to the distance calculation along with the ungraded codes. And there is so in this step there is no human. So the distance calculation part will give you quotient independent features, and now these features can learn a quotient independent model. Okay, so we do some more innovations on the features rather than a monolithic distance. So instead of computing just one distance, instead of converting this whole expressive feature grammar into just one monolithic distance, we compute these distances across feature categories. This is because this is guided by the intuition that we believe that each of the feature category may relate differently to the rubric, and a regression equation can learn different weights on these distances to be more expressive and to be more accurate in that sense. So the feature categories, as I expressed earlier, are basic control expression and all these, which you can go through our earlier work and figure out more about this. The second thing is because these features, these distances can have very different scales. For example, a bubble sort program is 15 lines of code, and a binary search is 8 lines of code. And the scale of these distances across problems may lie on different scale. So we need to normalize these features and bring them on a consistent scale so that we can really learn these models which are quotient independent. So we have done. We have a particular approach to normalize this, which is based upon the sum of features in the good set. We have tried a couple of more approaches, and I'll present in the experimental section that we do have more future work that can be done in this domain to improve the accuracy of the model. So coming to experiments. So we have chosen a fairly good data set, which comprises of 20 quotients, and these are divided into 2 sets. So we take 8 quotients in the model building part. So we divide 8 quotients into test and train set, and remaining 12 quotients we treat that as 100% test set to check the generalizability of this model. And there were total codes of 3524, and these are in 3 languages: C, C++, and Java. So we do a couple of experiments over here. The first one is the comparison of quotient independent with the test case baseline, that how does the new models do. The second is the performance of this quotient independent versus the quotient specific models. And the third is performance on unseen quotients. So these are the 3 main guiding experiments that we have done. The metrics that we look at, the first one is the Pearson correlation coefficient. And then we look at 2 additional metrics. And why this is important is because we are learning models which are across quotients. And because this is across quotients, so the distances can be on different scale. And hence, we can have a kind of a learning which have the same structure with the grades, but they are a bit off. I mean, they are scaled a bit from the main grade. So that's why we look at these matrices as well. So bias is simply the difference between expected and predicted, and MA is just the absolute of them, and then taking the average over that. So these matrices are important. These additional matrices are important because these distances are on different scale, and we are learning a combined kind of a learning over here. So these are the results. On the top, I've shown with all the quotients together, and on the bottom, it's just for the unseen quotients. So here you can see that this is the all quotients, and this is the unseen. So this is, when it comes to correlation, the quotient specific approach that I mentioned earlier has a correlation of 0.84 on this set, and quotient independent with normalization. When we apply normalization, has a correlation of 0.8. When we don't apply the normalization, we have a correlation of 0.76, and with the test case baseline, it's 0.0665. You can see very similar trend in the unseen quotient part as well. So this proves the generalizability. And when it comes to bias and ME, again, you can see that there is a gain of like 0.11 improvement with the test case baseline, and similar improvement in the unseen problems as well. Similarly, if you look at MA, quotient specific has 0.41, quotient with normalization has 0.85, and without normalization has 0.66, test case baseline has 0.85. This is again a big improvement, which is 0.27 points. And there are a couple of more things to note here. So an important part that I want to point here is that with normalization results are much better than without normalization results. And this is because of the fact that I was explaining earlier, that these could have the same structure, but because we are learning a model which is across quotients, so we need to look on these matrices as well. So concluding this, now we have built a scalable machine learning models. And earlier in the quotient dependent or in the quotient specific models, we used to, it used to take around 4 to 5 months earlier. And now, because we just need a few good codes, and these good codes can be obtained automatically using test suite, we just take around 2 to 3 weeks to build a machine learning model for any new quotient. The second thing is that this model is live in production. This was a problem that we have faced while working over there, because we have to release probably 20, 30 quotients every 2, 3 months. And this is a problem that we have over there, and this is how we tackle this. The third thing is very interesting because this approach is a kind of a semi-supervised learning. This can be extended to other domains as well. It could be extended to probably math proofs or probably to circuit solving and all. and also to other kind of domains where identifying these good codes may not be automatic, but it's a human intelligible task, and cloud sourcing can be brought in to do this. So that's all. So we have a group which is based in Gurgaon, India, and the web page is research.aspiringminds.com. If you are interested, do get in touch with me anytime, and you can write us on these email addresses as well.
When you were talking about the time it took to set up the grading for questions, or used to be 4 and 5 months, now
Sure.
it's 2 to 3 weeks.
Yeah.
In each case, how much of it is manual time and how much of it is just machine time to process the data?
So this is, I'm just talking about the manual time. Machine time, I'm not even counting in this. Because of the fact that grading these questions is, it's a very, very expert and very specific task. So getting those experts in line and then getting these grades is a very, very expensive task. So I could just give you a number that, for example, if you have to grade, if you have to build model for one question and in 3 languages, then probably will require around 250 codes for one language. And we usually take we usually take 2 experts to have the grades, and it could be like around 1,500 to 2,000 grades per question. So that's why it was like a very time-consuming process.
Thank you.
Do you give any additional information to the student in addition to the score, or is it just the score?
Right now, it's just a score, but this is, this work is definitely extend. We are aiming to give feedback to candidates as well. So the larger aim is to, this whole domain of ML-driven education, in which somehow we can make content automatically. Somehow we can make these assignments automatically, and then we can grade them and also give them feedback. So this makes a loop which is this whole ML-driven education, and this can really change the discourse of education across the world.
Hi.
Hi.
So one question that I had was that you gave these examples of binary sort, and you said you showed this discriminative feature, right?
Yeah.
Now in this automated feature extraction and sort of identification, if you started with enough good examples of binary search code, do you find the same features that a human would, looking at the code would identify? Are the features interpretable in any way?
Yeah, these features are extremely interpretable, because we do know that while grading the assignments, if you ask a teaching assistant, he do know that what are the features that he want to focus on. And these are usually the features like whether he has got the control context right. So whether he has got all the fors and all the ifs right in their place. And then the next thing to look at is that whether he has got the data dependencies correct, whether the I in the first loop is correctly connected to the J in the second loop, and all this.
So your algorithm, the machine learning approach, can be reversed engineered to identify and tell a human that, these are the things that they should focus on. I guess
Definitely, because so this depends upon the modeling technique that we are using. So right now we have not looked into this, but this is really interesting to look at that whether we are able to get the right, whether the machine learning approach is able to capture the correct features or not. But this is like definitely interpretable work, because features are very, very interpretable, and definitely, higher weights on the regression equation can tell you which are the important features.
Thank you.
Hey, thanks for the great talk. My question is almost very related to his question. So his question was more like, hey, if I take one binary sort program, there are probably 20 versions of it, and how do you kind of cater to those 20 different variations?
Yeah.
My other question is more like your comparison between your 2014 work and 2016 work, where now it's more question independent. So I wanted to understand how your single model is scaling to different problem complexities. Like you gave us examples like, binary sort and stuff like that, but there could be more complex programs that are out there in the testing world. Mm-hmm. So I was wondering, like, how do you really scale up to those? Like, for example, Kagels of the world, or somewhere really there are some programming competitions versus just testing some college level entry students for their programming skills.
Yeah.
So I just want to get your feel on what level this scatters.
Sure. So just to maintain brevity, we have not presented the kind of programs that we can test this on. but we have really tested it on a wide variety of programs, including programs that has data structures, trees, graphs, etc. And this technique is agnostic of the fact that how complex is the program. Until it's an algorithmic problem, I mean, this technique can totally work with it. And regarding your second question, that how do we convert the specific to the independent part? So this is like I told you in the presentation. So we have these specific features, and we have to convert these features into something that can have the same structure across quotients. So this is the one such feature is the distance metric from that particular quotient's good codes.
Okay, thanks.
So my question was, does your algo also have, does your feature also have this time complexity also in it? So you may get the exact test results as out, but it takes more time. So are you also putting that in your score?
So that was like a foresight, because so what happens in our company is that we usually the production system precedes the research papers and all. And right now we are just bringing this thing into production, and we have tested it, and it works really good. I mean, it works fairly good.
No, what I'm asking is, let's say if the question was to sort a list, right? And
Sure.
You implemented by bubble sort and you got the right results. I implemented by merge sort.
Yeah.
Does my score would represent that my sorting algorithm was faster than you, and although we both score 100,
so
but I might get a better
so
score.
this technique is definitely very capable of doing that. But why we are not doing that is because we do have deterministic methods to evaluate complexity and all. So but that aside, so if you, I mean, technically or probably if you think through intuition, this technique can definitely identify between the two approaches. It depends upon how the humans grade these codes.
I just want to, I think you just, in the answer to the last question, you said, unless there is an algorithmic issue. I think what you're talking about is an algorithmic issue. Sort versus sort via bubble sort. I mean, do you first say which one it is, and then you use the features for that particular sort of good answer set?
So I have to maintain simplicity. So one thing that I have not shown in the presentation is that how do we capture different implementations of a program?
Yeah.
Right. So I can just come back to this slide. This is a very good question. So this is a slide, right? So here I have shown just one good code, because probably a bubble sort can be solved in multiple approaches, right? One could be recursive and one iterative. So in that sense, there are two different clusters of these good codes. And when we take distance, so we have the algorithm to take the minimum distance from these codes. But we don't take the minimum distance. We do some more innovation over there. To cancel noise, we take the minimum of the first 25 and all this stuff that we do. But this approach does incorporate this very practical fact that the same quotient can be done in multiple approaches.
And what if you have just one code, like one good code, and all the other codes it's a difficult.
Then it won't work. Yeah.
No, he has to prepare, I think, a whole bunch of.
Yeah. So this thing assumes that you have collected enough data so that you have enough good codes that can solve.
Okay, last question.
Okay. So you moved from having human graders to just using test cases to tell if a code is good or not.
Yeah.
So the one thing human graders could do is they could have stylistic or readability
Sure.
points.
Sure.
How would you eventually add back in some human graders to measure this, or how do you handle that?
So that is a completely different problem altogether, and we are working into it. So in terms, if you talk about the stylistics or the readability of the code, then in that sense, I think these type of features will not make much sense. We have to get different type of features like the comments or probably the size of variables and whether those variables are meaningful or not, all this. So that is a totally different problem, and that can itself be solved through machine learning. There is no it's possible, and we are doing that as well.
But those features are all problem dependent then. So you're
Yeah.
you know that you need 3 variables to solve bubble sort well or something. Can you build a model, question independent model to do that?
So there are some features which could be quotient independent as well, like number of comments or probably the size of variable names. But yeah, so this is a challenge that there are some features which are definitely quotient dependent, and I mean, yeah, this is something which is future work, and we'll definitely look into this and want to look into this in the future conferences.
Thanks.